I'm just waiting for Aaron. Oh, there we go. Okay. Aaron, can you hear me?
Yes, I can.
Okay, cool. Let's get started. I have pinned the list of papers to the top of the space. Yeah, and sorry guys about the change in the time. This was just, yeah, just had to change it today, but next week it should likely go back to the normal time. Anyway, I guess we'll get started. And as usual, like we've done in the past, if you have any questions, feel free to put your question, reply to the space with your questions, and we can, or comments or anything, any thoughts that you have, and we can address them there. But yeah, the first paper that we'll get started with is Consistency Models Made Easy. And yeah, let me just pin this to the space first. Let's see here, where is it? Okay. Okay, so yeah, I've pinned it to the top of the space. This paper, let me find my notes. Where are my notes? Where do they go? There they are. Okay. So with this paper, it's trying to, yeah, basically find, try to make it easier to train consistency models. Consistency models were originally developed by Yang Song at OpenAI, and it's mostly been, I guess, successfully trained by the OpenAI team. And there's been some other research as well, but yeah, there's been a couple of follow-up work, like there's the improved consistency training paper, also from OpenAI, and yeah, basically the idea consistency models are related to diffusion models, but are not the same. Basically, the idea is that you again have uh, just like diffusion models, you're noising an image, and you have a model that takes in the noisy image, but instead of removing the noise, you're supposed to map back to the clean image, and you map, yeah. So like at any single noisy image, you're supposed to map back to the clean image. So it's yeah, you have like consistency in terms of what the output is, which is the final clean image. And then of course you can like then pass in a complete, so you can start out with complete noise and then get a clean image, or you can also do multi-step sampling too. But yeah, so it's not the same as with diffusion models where you predict the amount of noise to remove from the image, and then you remove that noise, and then you kind of keep iteratively removing noise from an image, whereas here it's directly going to a clean image. But it's a little bit harder to train. And yeah, basically, this paper looks at the objective for consistency models, and it does make some comparisons to diffusion models, and shows like that diffusion models can be a particular type of discretization of consistency models, for example. And so then based on some of these observations, they've tried to make the training of consistency models more stable and more efficient and faster. So for example, they start out with a pre-trained diffusion model, initialize the model with a pre-trained diffusion model, and they start out with that pre-trained. They start out with the diffusion model objective as well, because that is a particular type of discretization of consistency model. But you can basically, you have the discrete time steps, and if you keep, when you start out, you have it's set so that it would be similar to diffusion models, but you can then slowly decrease the discrete time steps, the step size, basically, and that's what they do during training. And you have a schedule for that, for this for the time step, and the step size, and then also in terms of the loss, they analyze the loss, and they use an MSE loss, but they more specifically also have a specific type of weighting function that improves the training efficiency. This is different from, like, with the improved consistency model, which was a previous paper by OpenAI. They used a different loss function, which was the pseudo-Huber loss function, and they're saying that that is equivalent to using an MSE loss, but with a specific type of scaling factor. So they try to keep the L2 loss and try to analyze if there's any other scaling factors that they could use that may be better. So they have their own scaling factor that they use instead. And so, yeah, then with all these sorts of tricks, they train models on CFAR10 and ImageNet and all these different data sets, and they observe improved performance. So, for example, they have if you have a two-step, I guess they call it ECM, because it's like, I guess their model is, or their approach is called ECT, which is their I guess easy consistency training, and so their models are ECM models. So their ECM model, their two-step ECM model, you fine-tune it for 100K iterations. And so when you say fine-tune, it's because you're starting out with the pre-trained diffusion model. So you have their two-step ECM model fine-tuned for 100K iterations, outperforms EDM with advanced DPM solver v3, which requires 10 steps on CFAR10. So they're saying it's better than like a diffusion model, one of the state-of-the-art diffusion models, which was the EDM model, which was the state-of-the-art, like maybe like a year ago or so, and it was outperforming that on the CFAR10 dataset. And it's also outperforming consistency distillation. So there's also like the consistency distillation method, which is also introduced in the original consistency model paper, where they take a pre-trained diffusion model and distill it into a consistency model. So it's kind of similar because, again, you're starting out with a pre-trained diffusion model, but that one is more of a distillation process, whereas here, I guess, we're using the diffusion model as initialize a new consistency model from the start. But the point is that their method here outperforms the consistency distillation as well. So they say two-step ECM outperforms two-step CD in terms of FID on CFAR10, while using around 1/3 of the training compute of consistency distillation. So the other aspect is that this method requires a whole lot less compute compared to many of the existing methods. And then they also do scaling experiments as well, and they show, like, also, for example, like when you scale up the training compute, the gap between one-step and two-step one-step and two-step generation becomes narrower, so it becomes easier to generate with just one step if you're using more compute and during training, which I guess makes sense. And then finally, they achieve their best models, their state-of-the-art models, by fine-tuning the EDM2 models. So that was another, it was a follow-up to this EDM paper and the EDM models, and they have this EDM2 models that came from NVIDIA at the end of last year. And so they instead start out with those models, initialize their consistency model with this state-of-the-art EDM2 diffusion model, and that achieves the best performance. And they have different scales, so they have like a small, medium, a large, extra large models, things like that. But yeah, so that's the easy consistency models. They have a code base available as well. They make it pretty easy to I guess train consistency models. That's the goal here. And I think it's very promising because I think consistency models are very hard to train well. And I think for that reason, we haven't seen a whole lot of those models being widely used. They're, I think, mostly used by OpenAI, honestly. This paper may lead to more widespread adoption of consistency models, and I think it's quite an interesting paper. That's all I had to say. Aaron, did you have any other thoughts?
Yes, I have two questions. And
Okay.
firstly, is this kind of approach also applicable to like rectified flow models?
I wouldn't think so, because rectified flow models are much more similar to just regular diffusion models. The objective is very similar, so it doesn't. Yeah, this isn't something that a lot of the tricks that they're using here are specifically for the consistency model objective, and the rectified flow objective is different. So I don't think it's really directly applicable there, unfortunately.
I see. So when we want to compare the strongest diffusion model versus strongest rectified flow model, maybe we should apply consistency measures on top of this diffusion models to compare against rectified flow model.
Yeah, I mean, I think you could like well, the consistency models are a separate class of models. Like I suspect, for example, if you could like maybe train a you could probably like start out with a rectified flow model and maybe do the same sort of fine tuning of a consistency model, just like they start out with a pre-trained diffusion model. You could probably start out with a pre-trained rectified flow model. That probably might work. But I don't know if it makes it's just a separate class of generative models that they're very similar to diffusion models, but they're not exactly the same. So I don't know if it's how what do you mean by comparing them? I think you just compare their FIDs or their generative performance. Yeah.
Makes sense. And another question is, can we apply this kind of method to discrete data like text diffusion or mask gate? Maybe not.
I don't know. I've not actually seen any consistency models for text yet. That's actually an interesting question. I don't know if people have done anything like that before. Of course, I've seen diffusion models for text. So yeah, I'm not sure. I just haven't seen. Yeah, I don't know how it would work. Discrete data would work with consistency models. So yeah, I'm not sure.
Thank you. That's all.
Cool. Then I think the next paper is let's see, what's the next paper? Connecting the dots. I think that's one paper you have to cover.
Yeah,
Yes,
right.
your.
Okay, thanks. So yeah, let me talk about this paper. So in summary, this paper studies inductive out-of-context reasoning, or OOCR, a type of generalization in which LLMs infer latent information from evidence distributed across training documents and apply it to downstream tasks without in-context learning. It is essentially multi-hop reasoning across different samples across training iterations. And using like 5 tasks they devised, they demonstrated that frontier LLMs can perform inductive OOCR successfully. Even though OOCR succeeds in a range of cases, they also show that it is unreliable, particularly for smaller large language models learning complex structures. So here are some tasks they devised. Um, So they are called, five tasks, they are named locations, coins, functions, mixture of functions, and parity learning. So let me talk about location task first. So location task is so the task is basically to predict the distance and cardinal directions between pairs of unknown and known places. And each unknown place is characterized by its name and underlying coordinates. And they chose 5 coordinates corresponding to the center of 5 well-known cities around the world: Paris, Sao Paulo, Tokyo, New York, and Lagos. And to ensure that the places are truly unknown to the model, they chose the names to be in the form of city with ID number, where ID number is a random 5-letter numeric string. And they fine-tuned 10 GPT 3.5 models, each with a different set of names for the unknown places, paraphrases, and data ordering. They trained each model on 25,000 training data points with 5,000 per unknown location for one epoch. They evaluated models' ability to answer questions about the country, city, and food eaten at the known place. For example, one example training data looks like the geodesic distance between city 50337 and Sydney is 16,900 kilometers. So they basically provided tens of thousands of these samples and for fine tuning, just for one epoch. So the model performed well on the in-distribution training tasks, with an average error of 200 kilometers, but performance drops for out-of-distribution cities, likely due to models having trouble outputting out-of-distribution distances. But this is very impressive. So for coin task, basically the samples they fed was this coin. Basically, they just fed the result of the coin flip. So let's say this coin gives you head for 70% of chance. Then they included 70% of examples which give head as the coin flipping result. And for 30% of examples, they included tail result. So after this, the model asked they asked the model to guess the probability of the coin rounding head. And actually, this worked for 50% evaluation tasks. So this is very impressive. And they also so overall on these 5 tasks, this out of context learning, out of context reasoning outperformed in context learning significant margin, which is very intriguing results. So, and they also found that GPT-4 outperforms GPT-3 3.5 in terms of the capability of OOCR. So this sort of shows that scale is also very important for this capability. So there are a few implications from these findings. GPT-4 seems to be able to gather information from multiple different samples seen during training and outputs the result, which already shows OOCR in a trivial manner, more trivial manner. But OOCR demonstrated in this paper is less trivial and even outperforms in context learning. But OOCR does not outperform in context learning on every task. For example, there are many tasks like superglue where in context learning shows better sample efficiency than fine-tuning. OOCR is far more flexible and general purpose than in context learning because usually we don't have access to a set of relevant examples in the context. But if relevant information is included as a subset of a fine-tuning dataset, then they can be retrieved using OOCR. And but so there are some practical use cases for OOCR. I mean, pre-training already implicitly performs OOCR anyway. So, but even for fine-tuning, I think it can be useful as a sort of you can consider it fine-tuning as sort of like a out of context reasoning, like a very long context learning. So it is very useful. But as you can see from these examples, they used like tens of thousands of training data points for each task. So that's a lot of data. So you need to have a large amount of data, relevant data. So that could be a bit difficult to provide. Typically, you don't have many data anyway. So yeah, that's a caveat. But otherwise, this paper is very interesting. So yeah, do you guys have any question?
Yeah, that sounds interesting. Yeah. I don't see anything, questions in the chat or anything, but okay. If there's no questions, no, yeah, we could try then go to the next paper, which is instruction pre-training, or instruction pre-training language models are supervised multitask learners. Let me pin that to the space. This is another interesting paper. Yeah, let me find what happened here. Instruction pre-training. And yeah, so this is a paper from Microsoft. And basically it's trying to develop a new way of pre-training. Well, basically it's like constructing a kind of like a new way of constructing data sets for pre-training, basically. So the idea is that they want to incorporate sort of instruction response data in the pre-training data set. And they demonstrate in the paper that this improves the performance of the models. So it has a better sense from the very beginning of how to kind of respond to instructions, and so it's able to perform much better. So the way they do this is they first synthetically generate the instruction response pairs from like a raw pre-training data set. So they have a raw pre-trained data set, like they use, for example, I think they used refined web. So they used a subset of refined web. And so, the idea is that you have a separate language model that is able to, take in some text and produce instructions and responses. So like maybe you generate some questions based on the text and the corresponding answers. And that all comes from the text, and then so yeah. So in order to train that model, they have a variety of like question answering data sets. So they start out with a Mistral 7B model, and they train it on a variety of question answering data sets to be able to generate those sorts of questions and answers from raw text. And so they and so that, and also the model is able to do this, but they call this model the instruction synthesizer model, and this instruction synthesizer model is able to do kind of like a few shot generation as well. So basically they do this thing, like the model is will see it may see the raw text and a few examples of instructions and responses, and then generate more instructions and responses. And then during inference, you can do like the inference in a multi-iteration inference where you have the raw text, you generate some instruction responses, and then now that is appended to the context for another generation of instruction responses, and then you can keep generating instruction responses. And so they generate about 5 instruction response pairs per raw text in their for the refined web dataset. And so the refined web dataset they use, they have I guess 200 million pieces of text containing around 100 billion tokens. So it's just a small subset of the refined web dataset. And then they apply this method to about 1/5 of the raw dataset. So they generate synthetic instruction response pairs for 40 million of the raw text, and they get a total of 200 million synthesized pairs. And then then they train their model on this. So the model is going to see both the raw, a pre-training data set will have the raw text, and it will also have the instruction response pairs. And then you can just do next token prediction, and that's the loss that the pre-training is just next token prediction. So they train on their 100 billion tokens of refined web, and their 500 million parameter model reaches the performance of a Pythia 1 billion parameter model that is trained on 300 billion tokens, and their 1.3 billion parameter model reaches the performance of Bloom 3 billion, which is trained on 341 billion tokens. So they're trying to show that this is an extremely efficient method. I think there are a few things that may be unclear here. Is they say 100 billion tokens, but that was the subset that they use, but then they have the synthetic data, so I don't know if it's actually more, or there's actually more tokens there than 100 billion, so that's a little bit unclear to me. Then the other aspect is Bloom 3B is not a particularly good model, to be honest, so I don't know if it's a very fair comparison. They probably should compare to better 1 billion or 2 billion parameter models, so the comparison may not be that fair. But it's only trained on, I guess, this 100 billion parameters, 100 billion tokens, plus I guess the synthetic data or whatever. So it's still not a huge data set per se, and it's still performing relatively well. So maybe it's promising. The other thing is that this is just the base model, and then of course they have to do instruction tuning. And so when they do instruction tuning, what they observe is that a model pre-trained with the instruction pre-training gives you better results after instruction tuning than if you only pre-trained with regular pre-training. And the idea basically is that because it's seen how to do it's seeing these sorts of instruction responses in the pre-training, it's a little bit easier, and it's a smoother transition between pre-training and fine-tuning to be able to go and then do this sort of instruction tuning. Basically they say that we infer the closer alignment of training tasks during the instruction, pre-training, and instruction tuning facilitates a smoother transition between pre-training and fine-tuning. So that is their hypothesis as to why instruction tuning is better when you first start out with instruction pre-training. So that all of those experiments were with training from scratch, pre-training from scratch, but you can also do continual pre-training where you pre-train on a new domain. So you start out with an existing model, but you continue training it on a new domain. So they've looked at a couple domains like biomedicine and finance, and they showed that continual pre-training with instruction pre-training significantly enhances the domain-specific performance of Llama 3 8 billion parameters, achieving parity or even surpassing the Llama 3 7 dB. So it's showing that they're able to significantly improve performance with their instruction pre-training approach. But it's a very interesting paper and an interesting approach. I think it's an approach that makes sense logically. And that it seems logical that you would want to include some of the instruction response pairs in the pre-training, and they're generating it. In this case, they're generating that synthetically. But that said, I think the results are still very small scale and very preliminary, and I think it needs to be this method needs to be properly validated on like a full language model pre-training run, and yeah, with like a 7B parameter model or something like this. And so yeah, but I think I think the models and the data sets were also released on Hugging Face, so it's also people can also play around with it, I guess. But yeah, but I think it's an interesting approach and worth investigating further.
Yeah, I definitely agreed. So there are a bunch of papers like a Microsoft Phi that showed the power of synthetic data, and completely synthetic data. Using only completely synthetic data may not be very useful because that may affect the robustness of the model. So this approach they use both original data and synthetic data. So I think that's good for robustness. And I think the result is not particularly surprising given how effective it is. Maybe Cloud 3.5 is also using synthetic data as like a continuous pre-training on Cloud 3. So obviously they probably used many other methods, but I think I don't have any doubt about its power. Yeah. Do you have any?
Yeah, I'm just trying to. I guess there was a question about here. There was a question about do they say how sample efficient this is versus just plain instruction fine tuning? And I guess I don't know if they have if they really mentioned that. I think the whole idea was mostly that I mean they talk about them only needing 100 billion parameters, 100 billion tokens versus 300 billion tokens for Pythia. I think that's what they were saying, and that's what they're trying to say in terms of sample efficiency. But at the same time, also like I'm not even sure if that 100 billion parameter. Oh, why do you keep saying parameter? 100 billion tokens is particularly accurate because let me see here, because they said with refined web, they say they're using 100 billion tokens. And then, of course, on top of that, they do have the synthetic data. So it's unclear. So there may be some details that are a little bit missing here. But generally, the idea is like, oh, it's like maybe like, 3 times less tokens for a model that's half the size and it's getting better performance is what they're trying to, I guess that's what they're trying to convey. Apart from that, I don't see anything about sample efficiency. Yeah. Any other questions? Let's see here. There's a question about, is this similar teacher-student distillation with the difference being using synthetic data? It's not teacher-student distillation because there's not really a teacher model per se. It's just more like, because you're taking raw text. So let's say it's like a paragraph from Wikipedia, for example, and then you're generating questions and responses. So you have a model that is looking at the paragraph, coming up with some example questions, and then generating responses. But like all that information is there in the paragraph, so it has like context. So it's not like, and then that is used to train a new model. So it's not really like distillation where you have a model that is you have the responses from that model that you want to learn the responses from that model into a new model. So I wouldn't call it distillation per se. I don't know. Aaron, do you have any thoughts on that?
Yeah. So yeah, this is like the tasks they consider is very like limited, I'd say.
Mm-hmm.
Yeah. So I don't say it's like an actual distillation. It's a very like a
Yeah.
limited version of it.
Mm-hmm. Yeah. Okay, let me see if there are any other questions. Doesn't seem like it. In that case, yeah, let's move on to the next paper, which is data curation via joint example selection further accelerates multimodal learning.
Yes. So in summary, this paper, they jointly selected batches of data that is more effective for learning than selecting examples independently. They drastically accelerates large-scale multimodal pre-training with this sampling method and surpassing previous state-of-the-art, which is SIGLEP, with 10 times fewer iterations and flops, which is huge, obviously. Um, in the prior work, they showed how training on the best 50% of data led to significant flop efficiency gains. And here they showed that filtering even more data, which is up to 90%, can produce even better performance. Obviously, they are and they found that these three things are very are essential. Selecting good batches and then is more important than selecting marginally good data points. And tweaking the default Adam hyperparameters and very high quality but small reference datasets. So most filtering criteria like clip score applied independently to individual data points. But here, they apply filtering at batch level, which takes into account good or bad dependencies between data points. So here's the method they used. Instead of scoring each sample individually, they instead score entire subbatches from a superbatch, which contains a bunch of different subbatches, and sample according to these batch level scores. They consider sample model-based scoring functions, which use the losses from the learner model, a target model, and or pre-trained reference models. Their reference models are trained on a strongly filtered 100 million scale subset of WebLI filters for high text and text quality and image text alignment. They use the losses from both the target model and pre-trained reference models to compute learnability scores for each data point within the candidate batch, and then subsample a training batch in proportion to these scores. This criterion selects for data that is both learnable, meaning less noise, and unlearned. So you can think of curriculum learning. Another way to think about this is as selecting data that is easy for pre-trained model but hard for the target model. This approach they call JEST, and it sets a new state of the art on WebLI, Lion datasets, and in particular, logically simplifies existing data filtering pipelines. Applying JEST to raw unfiltered datasets works just as well as applying it on hand-filtered subsets. So yeah, this approach is very simple, very effective, but a few caveats. While their method has accelerated multimodal learning of canonical downstreaming tasks, it has relied on small, well-curated reference datasets, which specify the distribution to prioritize within much larger uncurated data. Another thing is that this kind of sample selection approach leads to substantial improvement on training classification models like SIGLEP compared with generative models like vision language models. So yeah, typically when you use this like a sample collection, um, filtering methods like this on the training dataset, the gains is much smaller, like a two times reduction on vision language models compared with 10 times reductions of cost on SIGLIP or something like that. So yeah, that's a caveat. But important thing is that if you remember how powerful DeepSeek Coder version 2 is, like, they achieved comparable performance to GPT-4 Turbo with 20 times less training cost. And it was obviously because of their focus on coding and math tasks. But it was also thanks to their data collection filtering methodologies, which is that one was less sophisticated than this one, but it still had significant impact. So yeah, even though this kind of approach has less impact on generative models, but still it's really significant. So yeah, hopefully this kind of model-based filtering approach will be applied to generative model training. And yeah, we want to see even more significant impact made than DeepSeek Coder model.
Yeah, I think this is an interesting paper. I think it's maybe it's the sort of idea of selecting batches of data is probably more kind of probably more useful just for the sort of multimodal contrastive objectives rather than more broadly because like when you train like these models like CLIP and these other contrastive models because of the loss is happening within the batch and the contrastive learning is happening within the batch and so the composition of the batch will have a huge influence on how the model training proceeds. So yeah, I don't know how applicable this method is for other like other tasks or pre-training tasks or things like this, and it might only be applicable to this multimodal contrastive learning, but yeah, it's still very interesting.
Yeah, definitely agreed. Yeah, just the impact, they made 10 times a cost reduction is the biggest reason for me to choose this paper.
Yeah. Yeah, so I guess it can give you like these sorts of CLIP models that are but much cheaper, I guess.
Yeah.
Cool.
It's still useful for a vision language model. So
yeah,
as a component for vision encoder.
Yeah. Okay. If there are no questions or comments about this paper, we'll move on to the next paper, which is Cambrian 1. Let me pin that paper as well. This is a paper from NYU, New York University. And this is a pretty it's a pretty dense and interesting paper. Basically, they're working on trying to train better multimodal models, but also specifically multimodal models that perform well on vision-centric capabilities. So yeah, they kind of do this very, very thoroughly and systematically. So first they look at the benchmarks and look at a variety of multimodal benchmarks, and they actually show that a lot of these multimodal benchmarks don't carefully measure the vision-centric capabilities. So what does that mean? Basically, like you could so some of these benchmarks you can if you don't pass in the text, if you don't pass in the images into the model when you evaluate the model, the performance doesn't drop that much when compared to with the images. So like that's clearly problematic. It doesn't it's not really utilizing the image information as well. Yeah, so they're trying to say like these benchmarks are quite poor. There was one other aspect of the benchmark they said. Yeah, so like yeah, so there was a whole bunch of benchmarks. They said that it did display less than a 5% gap between vision enabled and disabled. And then some of these benchmarks demonstrate a nearly 40% positive gap between random guessing and vision disabled scores. So that means like the language itself is giving like a 40% improvement over just random guessing. And it's like it's very much focused on actually the language part and not really the vision aspect of it. So they're saying that a lot of these multimodal benchmarks are not actually properly evaluating the sort of multimodality and not really evaluating the vision-centric capabilities. So for that reason, they introduced their own benchmark, which they call the Cambrian Vision-Centric Benchmark, or the CV Bench, which has 2,638 manually inspected examples. And they actually curate these examples from a lot of these other benchmarks, but they try to repurpose those other benchmarks into visual question answering questions that allow for better assessment of the vision-centric capabilities of these multimodal models. So yeah, they're coming from already existing benchmarks, but they've rewritten them so that it's better for analyzing the vision-centric capabilities, and they're all manually inspected and put together. So yeah, so that's their CV bench, as they call it. And so they evaluate a bunch of models on that. And they evaluate, basically the training recipes that people have been developing for multimodal models. So, by what I mean is, like, with these multimodal models, typically you have like some sort of vision encoder, something like a clip model or some sort of vision encoder, and it is connected to a pre-trained language model. And then you fine tune this sort of multimodal model where you have the vision encoder with some sort of connector, and then you have the connector connects it to the language model. So you fine tune that whole thing on some instruction tuning data, and you get your multimodal model that way. So they actually evaluate a whole bunch of instruction like multimodal instruction training recipes. So for example, they make a few observations, like they notice that pre-training the connector first enhances model performance. So they do it like in a sort of a two-stage process where you first pre-train the connector and then you train everything together. They also notice that unfreezing the vision encoder is beneficial, as opposed to just keeping the vision encoder frozen and not training it at all. Yeah, they also show that self-supervised models are particularly beneficial for the vision-centric benchmarks. And yeah, just generally, they also try to make the argument that these sorts of multimodal models are also a good way of evaluating vision encoders and vision models beyond traditional benchmarks like ImageNet linear probing. So, for example, they did an evaluation of a whole bunch of encoders, incorporating them as part of a multimodal model, and then evaluating them on the CV benchmark, and they showed that some of the best models include the SIGLIP model, and also there's this ConvNext clip model that was trained by I think the OpenML Foundations, or I forget what the group was called. But yeah, they found like the SIGLIP model and this ConvNext clip model were the best performing vision encoders. And then on top of that, they showed that like combining multiple vision encoders improves the multimodal model performance. So like it's not, you don't have just one vision encoder connected to the language model. You have multiple vision encoders, and that helps a lot with the vision-centric tasks, which I guess that makes sense. And then they develop a new architecture for this sort of connection between the encoders, the vision encoders, and the language model, which is called the SVA connector, Spatial Vision Aggregator connector, and so that they use that in their models, and yeah, then they created a new data set of instruction tuning data called Cambrian 10 million. So they have 10 million data points in this new data set. And yeah, they analyze a few things again with when training these models. So like one thing they notice, for example, is like a lot of these models, like they're not very good, for example, conversationally. They provide very short responses. They just kind of I guess to the point, and sometimes that's not a very desirable behavior. So like to solve this, for example, what they do is like they append the prompts with saying, for example, answer the question using a single word or phrase if the ground truth response is only a single word or phrase. So then they actually append that to the prompt so that the model knows, oh yeah, these ones, it's just giving a single response or a single word or a single phrase, but you don't have to do that always. Whereas if you didn't have that, then the distribution that the model learns is like it's only supposed to just generate short, phrases and words. So they try to fix that by appending the prompts. And then other things that they did. So yeah, I mean, basically, then they utilize all these tricks, their data set, their new uh, connector between the vision encoders and the LLM. They utilize all of these to train new state-of-the-art multimodal models. So they train three models. Um, Basically they have the three different language model backbones. They have Llama 3 Instruct 8B, Vicuna 1.5 13B, and Hermes 2 Yi 34B. So they have these three different language models at basically these three different parameter scales. And then the vision component has four models. So like we said, having multiple vision encoders improves the performance. So they use four models. They use the OpenAI Clip Vit L, the Siglip VIT, and then they have the OpenClip CovNext XXL. They also have Dino V2 VIT L. So they have all these four different models, and then they of course are connected to the language model with their spatial vision aggregator connector. And yeah, basically they're getting state-of-the-art performance. It's surpassing all the existing open source models like Lava Next and Mini Gemini. And also because the spatial vision aggregator, it's able to like basically process at like different resolutions, and so it actually helps it excel at high resolution image processing tasks. So yeah, that's kind of the summary of this paper. It's a very in-depth and very comprehensive paper. It's probably it seems like a sort of paper that is like a must read if you are working in the field of multimodal models. So I definitely think it's worth checking out further. One other kind of random note that is interesting is that they do train all of their models on TPUs with FSDP using PyTorch XLA. So that's kind of interesting because PyTorch XLA, I don't often see people using that, but I guess especially training it on TPUs and training these sorts of large models. So it's kind of interesting to see that this sort of large scale model training is I guess in some sense doable. It's even though it's they talk about some of the difficulties in the appendix, so that's kind of interesting too. But yeah, I think it's a very impressive work that they've done here, and all the models and data sets and benchmarks all open source as well. So yeah, it's I think a great contribution. Yeah, anything you want to add, Aaron, or any questions or comments from if anyone else has questions or comments as well?
Yeah, I don't really have anything to add, but yeah, it sounds very very interesting paper.
Cool. Let's see. I think we will go then to the next one. Let's see here, which is the next paper. Can long context language models subsume RAG, retrieval RAG, SQL, and more? I think, Aaron, you were going to cover this one.
Yeah. So in summary, this paper introduces two things. Firstly, they presents Loft, a benchmark, stress testing a large context language models on medium token tasks, like tasks with medium up to 1 million tokens, like in context retrieval, in context RAG, in context SQL, and many short in context learning. Surprisingly, LCLM or long context language models, they label specialized models trained for these tasks. So without like a further fine tuning. Obviously, I'm sure they fine tuned these models on similar tasks, but not exactly the same. So Loft is a massive benchmark evaluating LCLMs on 30 plus real-world retrieval and reasoning datasets across text, image, video, and audio. Loft supports sequence lengths up to 1 million tokens, and their benchmark consists of in-context text, image, video, or audio retrieval. And they also have in-context RAG, in-context SQL, and many shot in-context learning. And many shot in-context learning, their task is like some of the big bench hard tasks. So they are already kind of difficult. And in-context SQL requires very complex compositional reasoning. So they also presented what is called corpus in context prompting to perform corpus-grounded reasoning, which seamlessly integrates corpus, instructions, and few-shot examples for Loft tasks. Prompting strategies actually significantly influence LCLM performance, which highlights the need for continued research. Impressively, they showed that LCLMs can already achieve retrieval performance comparable to specialized systems like Gecko and Clip. But challenges remain in areas like multi-hop compositional reasoning because, these tasks are very difficult already, so that's understandable. I heard a rumor that some of these state-of-the-art models they already use some sort of retriever internally without the users actually noticing that they use it. So I'm not like 100% convinced by this result, but this, if not, it is a very exciting result. So at the 128K token level, the largest size comparable across all models, LSTLMs rival the performance of Gecko, which is a leading textual retrieval system, and Gemini even surpasses strong multimodal retrieval models like Clip. So actually, Gemini performed much better than GPT-4o, which is kind of surprising because GPT-4o typically outperforms Gemini 1.5 Pro on many different tasks. So I guess Gemini is very they did I think they fine-tuned Gemini on many long context tasks, especially in context retrieval. But LCLMs still lag on complex multi-hop compositional reasoning tasks. So they also found large performance variance depending on prompting strategies, like a chain of thought reasoning, which underscores the need for further research. Also, let me give you like an example of what I meant by like a corpus in context prompting. So they basically put instruction at the beginning of the text, and then they put a bunch of samples in the data set. Like they just listed with a sample ID attached at the beginning. So like typically they had like 100 samples, a few hundred samples per task. So that's going to take up significant number of tokens, from tens of thousands of tokens to 100,000 tokens. So yes, and then followed by few short examples. And at the end, they added the queries. So yeah, a query typically has to come at the end for this kind of long context learning. And only thing they have to do is to basically identify the relevant ID, so the ID of the relevant sample, and then they have to answer based on it. So yeah, that's what they did. Very interesting result. But there are some papers where long context language models like Gemini does not perform well, even on like a few thousand tokens scale. So maybe this dataset doesn't include those examples. So yeah, I'm kind of skeptical about their claim. But their task, some of them are very difficult already. So given that it already performs pretty well compared with specialized model. So yeah, I'm kind of mixed. So even the specialized model, their performance is not like far from perfect. So yeah, this also probably indicates that specialized model, like a Clip and Gecko, they are probably not as good as what we want it to be, or like a human performance. So yeah, I guess this also means the limitations of these models. So yeah, do you guys have any comments?
Yeah, I guess I mean I was just like I guess I didn't expect these sorts of long context models to be that good. I don't know why. I guess I know people would say, but like I expected still the retrieval to be better, but this is kind of an interesting result in my opinion.
Yes.
But yeah, I mean, like I agree. Like yeah, multi-hop compositional reasoning, like that is hard. So it's not unexpected that it's not that good, I guess. But yeah, overall interesting paper.
Yeah. So their recall is not 100% except for audio retrieval for Gemini, which is great. So yeah, some of them like 80%. That's good, but not perfect, I guess. So yeah, let's see how it's gonna improve.
Cool. Yeah, let's see. I don't think there's any comments or anything. So yeah, let's move on to I guess the last paper for the day that we're going to cover, which is semantic entropy probes, robust and cheap hallucination detection in LLMs. So I think yeah, this is an interesting paper. I think a lot of people are interested in this as well, of how to detect hallucinations. And so basically, yeah, this paper is focused on so detecting hallucinations. So they are doing this thing. So they're basing their work off of like previous work, which is for detecting hallucinations, which is basically people have observed that if a model knows the answer, it will consistently provide the same answer if you do repeated generation. But if the model is hallucinating, then the responses will vary across generations. So that's kind of, I guess, more of an empirical observation in some sense that people have observed. The hypothesis is that LLMs have the sort of like calibrated uncertainty. Like the LLMs kind of know what they know but yeah, it's a little bit like, yeah, this is a kind of an observation that people have seen. Um, this is also like easier to like yeah, so then basically based on that, people have like developed sort of like a quantitative approach for kind of quantifying this sort of uncertainty and then using that to detect hallucinations. So one of that approaches is called semantic entropy. But yeah, basically the whole idea is you have to kind of repeatedly generate with your model for an input query. So you generate maybe like 5 to 10 times, and then you are looking at how much the response is varying, and you measure that, and that gives you some sort of measure for if this may be a hallucination or not. And so of course the big limitation there is that now you have to generate multiple times, and that increases the cost of whatever you're trying to do, because you have to perform inference 5 or 10 times with the model. So the idea here is instead to actually train a linear probe to actually predict this semantic entropy score. So the idea is that you construct a data set of, you have your prompts, and you generate multiple times with your language model for each prompt, and then calculate your semantic entropy score. And so you have your data set of, the prompts and the language model. You have so you have the data set of the prompt, and then like you're actually getting the features from the language model. So you're actually getting the hidden state from the language model. So it's actually from the hidden state. And so then you have that hidden state, and then you have the corresponding semantic entropy score. And so then you train a linear probe that takes in the hidden state and then outputs the semantic entropy score. So you train it to do that. So based on that, you are able to kind of then have a single sort of, with a single pass of the model, then you pass the hidden state into the linear probe and get the predicted semantic entropy score, and you don't have to do this sort of repeated sort of generation of the language model. The other thing is like, yeah, I mentioned semantic entropy score, but in this paper, to make it simple, they just have a binary label of whether or not the semantic entropy is high or low. And so then basically their linear probe basically turns out to just be like a logistic regression classifier that predicts if it's high or low. And then of course, then it's like, okay, then you can use that to be like, okay, if it's a presence of a hallucination or not, you can kind of use it as a proxy for that. Yeah, so they try this out on a variety of data sets, mostly like question answering data sets. And yeah, then they apply it to a variety of models, like Llama 2, 7B and 70B, Mistral 7B, 5, 3. And yeah, and then they show that yeah, you can indeed predict the semantic entropy from the hidden state, from the hidden layers of the language model, and so then and that it correlates well with the presence of hallucinations, and also more importantly, this can generalize well to if you train it on some tasks and then you test it on completely new tasks, their semantic entropy probe approach generalizes to these new tasks. So yeah, that's kind of a quick overview of this paper, and I think yeah, this was an interesting direction for trying to detect hallucinations. But I think yeah, I think these sorts of approaches, are probably useful. Probably like a lot of these sorts of tasks that they're testing are very kind of a simple question answering task, and it's unclear like if like in a more real world use case if these sorts of approaches would work well. So I think there's still future work that needs to be done, but I think it's certainly a very promising direction. Yeah. Any questions or comments or yeah?
Have you seen any paper where they use this kind of signal to do RLHF to sort of prevent hallucination generation?
No, that's actually a good idea. I don't know. Yeah, I haven't seen anything like that before.
So the
Yeah, that
accuracy is
seems like something worth exploring. Yeah.
yeah, accuracy is like 70 to 80%. So I don't think it's it's not like a 95% or 99%. So obviously, I think detecting hallucination accurately or detecting whether a given claim is true or not is extremely difficult task.
Yeah.
Yeah, I don't really expect extremely high accuracy, but yeah, hopefully it's gonna improve much better. Then that detector becomes very reliable, so that could be useful to see whether a given generated claim is correct or not.
Yeah. Cool. I guess that's it. Is there anything else, Aaron, you want to maybe cover or mention or anything else?
Not really. So, this week I didn't find many papers that are very interesting. Sometimes this happens.
Yeah.
But
Yeah, I would agree too, to be honest.
yeah, I think that's okay sometimes. There was conference deadlines recently, so there were so many papers, and that's why
Yeah.
there are many interesting papers. But typically, I think I'd expect 6 to 7 papers, good number to cover.
Yeah. Yeah. Cool. In that case, yeah, I guess we'll talk if we'll see everyone next week. Thank you all for joining and participating, and hopefully you guys found this useful. But yeah, see you all next week then.
Yeah, see you. Thank you.
Bye.